All right, so I hope this is what you got for this question. C1, that is removable because the limit as x approaches C1 of f of x exists, so that's removable. C2, since this part is going down to infinity, that's an infinite discontinuity. C3, the limit from the left is a real number, the limit from the right is a real number, yet the limit does not exist. So when the limit does not exist, what we have is a non-removable jump discontinuity. C4 is an infinite discontinuity because the function is going up to infinity. And C5 is, since the limit exists and is a real number, that's a removable discontinuity. So we can additionally say about C2, C3, and C4 that they are all non-removable, but they have these sort of specific types of infinite and jump, the subspecies, if you will. All right, now it's a little confusing on the homework when they say, look at something like this and say, state where f is continuous. But we can use interval notation. F is continuous, and I can say on the interval from negative infinity to C1, union the interval from C2 to C3, union the interval from C3 to C4, union the interval from C4 to C5, union the interval from C5 to infinity. And all of those intervals are open because they do not include the endpoints of the intervals, because the endpoint of each interval is C1. I'm missing C1 to C2. So in here I should have union C1, C2. So it should go negative infinity C1, C1, C2, C2, C3, C3, C4, C4, C5, C5, infinity. Right? And they're all open intervals because, for example, we know that f of x is not continuous when x equals C3, so we want to make sure C3 is not included in either interval. That's why all the intervals are open. And of course, the ending intervals are open because you cannot include negative infinity or positive infinity as an endpoint of an interval. So that's classifying these continuities. So now what I was saying at the end of last video is, once you know that discontinuity is removable, wouldn't you like to be able to remove them? They're remove-able. You should be able to remove them. All right, so here's the kind of thing you're going to encounter. And this compares to your book, page 85, number 25 through 30, which I'm going to assign to you. So this is sort of, pay attention to this one for the homework. All right, so what I have is I have a function, and it has a discontinuity somewhere. It has a removable discontinuity. And what I'm going to do is give a formula for a piecewise function that is continuous. So the first thing I need to do is analyze this function to find out where is the point where it's discontinuous. So I need to factor the numerator and denominator, so it looks like I get x plus 3, x minus 2 in the top, and I get x plus 5, x minus 2 in the bottom. All right, so I know that f has a hole at x equals 2. So that's the discontinuity. We now, you've always been saying hole in your pre-calculus and your algebra 2. Now we can call that a removable discontinuity. So we can say f has a removable discontinuity at x equals 2. All right, well, so to remove the discontinuity, right, you want to think, I have x plus 3 over x plus 5, like how hard do I want to think about what that graph looks like? There's an x-intercept at negative 3, there's a vertical asymptote at negative 5, the y-intercept is 3/10. All right, so the graph, and there's a hole at x equals 2. So basically this graph, is x-intercept, y-intercept, horizontal asymptote at 1. All right, so this graph looks like this, but right here at 2, there's a hole. All right, so basically what we're saying is, how should I fill the hole? When it says give a formula so the function is continuous, how am I going to fill that hole? Well, to fill the hole, you just need to know what the limit is. So that the y value of the hole is the limit as x approaches 2 of the function. So limit as x approaches 2 of, I'll take the factored version since it's factored already, x plus 3, x minus 2 over x plus 5, x minus 2. Notice I did not reduce this expression because this expression would not be equal to the reduced expression, because this expression has a hole in it. The reduced expression would not have a hole in it, would not even have a removable discontinuity. We would have nothing to talk about. However, the limit is equal to the reduced limit. Limit as x approaches 2. That's why it's so important to, as I've been talking about some people with their homework, write the limit statement every time completely until you evaluate the limit. Now we're ready to evaluate the limit and say this is equal to 2 plus 3 over 2 plus 5. It's 5/7. All right? Limit. When I plug in the value, I'm really evaluating that limit by substitution. Now it's not a limit anymore. All right? I can, qualitatively think about, does it make sense that this is telling me that the coordinate of this whole is 5/7? Yeah, it does make sense because it's higher than the y-intercept, which was 3/5, and it's lower than the horizontal asymptote, which is 1. So we're expecting a number between 3/5 and 1, so that sort of bears out the validity of our work. All right, so now here's what it means when we say give a formula for a piecewise function that is continuous. This function that we are given originally has a removable discontinuity. But if we define a new function, if we define f of x equals x squared plus x minus 6, so just the original function, x squared plus x minus 6 over x squared plus 3x minus 10, when x does not equal 2, and 5/7 when x does equal 2. This function is continuous, and it's not only continuous at x equals 2, it's actually continuous for all real numbers. Because the only place that our original function was discontinuous was at the whole. Oh, that's not true, because the function is discontinuous at -5. So we actually cannot make it continuous for all real numbers. Here's what we can do, though. We can make this function continuous, and this is a nice phrase to say, on its domain. So, since x, no, that's not good either, because x equals 2 was not in the domain either. So I guess the best we can do is say we wanted that function to be continuous at x equals 2. Now, I've had to go through a lot of scratches and like, wait a minute, what am I doing? Why? Because this function actually has two discontinuities. It has a removable discontinuity at x equals 2. But what I did not think about when I wrote the problem is that there is also a non-removable discontinuity at x equals -5. And because it's non-removable, I cannot make this function be continuous for all real numbers, because that discontinuity is not removable. So this function is continuous at x equals 2. So in fact, it's continuous for all real numbers except x equals -5, if you want to look at it that way. But I think I've caused enough confusion. So I'll say normally the way we would phrase this question, give a formula for piecewise functions so that the function is continuous at whatever the removable discontinuity is, x equals 2. So what we do is we analyze the function, find the removable discontinuity, then we just find the limit of the function at that discontinuity, and then that limit value is what I put right there. And the number that I'm putting here is our limit point. All right? So that's removing a discontinuity, removing a removable discontinuity. So let's try that again. So here's another very common way that this kind of question is phrased. Phrased this way often on the AP exam, and it's phrased this way at least once in your homework. All right. I think, maybe not. All right. So what should k be so that f of x is continuous at x equals -4? You think about the confusing things I've said in this video and see if you can answer the question, what should k be?